Today we're looking at the A2 CCEA Physics Paper, Fields, Capacitors and Particle Physics, and it's the one from 2019. Let's get started. Question 1a. Define the farad, the unit of capacitance. Now, if you're stuck with this, always be thinking about the equation, the Q equals CV. Rearrange that for C, and you get Q over V. So capacitance, if you make everything 1, capacitance of 1 farad is if you get 1 coulomb per volt. Or you could say capacitance of 1 farad can store 1 coulomb of charge per each volt of PD across its plates. Part B. Two uncharged capacitors of 330 microfarad and 660 microfarad are connected in series with a resistor R and a 12 volt DC supply. A voltmeter is connected across one of the capacitors. The arrangement is shown in figure 1.1. Part 1. The switch is closed and the reading on the voltmeter increases to a maximum value of 8 volts. Across which capacitor is the voltmeter connected? You must show clearly how you obtain your answer. So we're told that this voltmeter ends up at 8 volts. So when two capacitors are in series like this, the charge stored is the same. So if we label one C1 and the other one C2, and this 8 volts will be like V1 and the other one will be V2. So we know from Kirchhoff's laws that the PD going into the circuit has to equal the sum of the PDs round the circuit. When the current stops, there'll be no PD across this resistor because there's no current. V across it would equal IR, but because I equals 0 at the end, it doesn't need to be counted. So the sum of these two voltages has to equal 12 when the current stops. So 12 volts has to equal V1 plus V2, which equals 8 plus V2, which means that V2 is 12 minus 8, which is going to be 4 volts. We can also say that charge is equal on the two capacitors because they're in series. And that means that C1V1 equals C2V2. Which means that C1 times 8 equals C2 times 4. Which means that C2 equals 2C1. And looking at the values of the capacitors, we can see that since there are two values, one which is double the other, we can immediately say that C2 is the 660. And therefore C1 must be the 330. Okay. Part 2 then, calculate the total energy stored by the two capacitors in series. So we know the voltages on them, we know their values now. It should be possible to use just a half CV squared for each one and add them together. So E1 is going to be a half C1V1 squared, and E2 is going to be a half C2V2 squared. So we just sub it in. Remember that this is in microfarads here, and we need to do that for both. So that first one comes to that, and the other one comes to this value. So we need to add those together, and we'll round that up to 0.016 joules. (2a) Explain what is meant by a field of force. So this is like straight out of your notes. You need to be having a learnt off statement for this. So they haven't been specific about the type of field. So we are talking then about an object with a special property. And this is a region where an object with that special property experiences a force. Golden rule here is if you can learn off a simple statement about how something works, then do that. Part B then shows us 3 examples of special properties: a negative 6 microcoulomb charge, a positive 2 microcoulomb charge, and a 4 kilogram mass. This is identifying the space provided, which point object could produce each of the fields drawn. Okay, so we've got an outward field and we've got an inward field. So firstly, gravity can't create an outward field, so this has to be the +2 microcoulomb charge, this first one, because remember, field points the direction that a positive would be pushed, and if there was a +2 microcoulomb at the center of this here, then positives would be pushed away because of repulsion. So this has to be the 2 microcoulombs. Now, this is the clever bit. The question is drawn in such a way that, both the -6 microcoulombs and the 4 kilogram mass will create inward field. However, the 6 would have to produce a stronger field than the 2, so the 6 microcoulombs would have to have more field lines, but this diagram has less field lines than this one. So if this represents the strength of a 2, then a -2 would have just as many field lines, and a -6 would have more field lines. So this has to be the mass. Part 2 then, compare and contrast the fields around point charges and point masses. So they're specific about that they want you to talk about point charges and point masses. So be careful when you're answering a question like this that you're answering what they've asked you. Firstly, as you can see, they are both radial fields. So when you look here and here, they radiate out in all directions. And they both follow the inverse square law. You could go into the fact that electric fields can be attractive or repulsive, whereas gravitationals are always attractive. You could go into the fact that electric fields can be shielded and gravitational fields cannot. Again, golden rule, lists like this should be learnt off. Question 3. 2-point charges -2 microcoulombs and +8 microcoulombs are placed 3 millimeters apart in a vacuum as shown in figure 3.1. Calculate the resultant force exerted on a -4 microcoulomb point charge placed at the point A halfway between the charges and state its direction. So we're calculating a force. This is where we need to be careful. Calculating a force, and it's on a negative charge. So we have equations that will give us the force based on what the -2 microcoulomb is doing, another force calculation of what the +8 is doing, and we'll get directions for both of those. So we can get those from the force between two charges equation, and when we get both of the values of the forces, we can look at their directions and see what has to happen with them. You should always draw these. You really should always draw these. Here on the left hand side here, we've got a -2 and a -4. They're going to repel, so the force on this that we get is going to be that way. On this side, we've got a -4 and a +8. They're going to attract, so the force will also be to the right, belonging, we call that force 1 and force 2. That force is going to be to the right as well. So we're going to get the magnitudes of these forces using the equation, but we will be adding them because they will have the same sign, or same direction at least. So we have the idea that F1 is going to be 1/4 pi epsilon naught Q1 Q2 over R squared. So just a shortcut here, your formula sheet in CCEA now includes a value for the entire 1/4 pi epsilon naught. So this is far better a value to use because it saves you writing in the 4 and the pi and risking some problem on your calculator. Just use this value. That's your top tip. So the important thing is be very careful here about subbing in these values. I would ignore the signs and get direction information from my diagram. So we can ignore the signs and just get the magnitude of these forces. So 2 times 10 to the -6, 2 micro, times 4 times 10 to the -6, and divided by R. And remember that R is 1.5 millimeters, and so we need to put in our 10 to the -3 and remember to square it, like so. And then we do the exact same thing for the other side. And again, substituting very carefully and remembering to get the right R and square it, like so. 4 micro, 8 micro, 1.5 millimeters, and it gets squared. Just need to move this up a bit. Gives us that for the first one, that for the second one, so we need to add those. And realizing we should probably only quote that to 2 significant figures because of the values in the question. And the direction is going to be to the right. Again, I can't overemphasize the idea that if you're working with things that are vectors, you should draw diagrams. It's very, very easy in this kind of question to get the directions of this wrong, or to just base your answers on the numeric values by putting in signs and thinking that you know what that's telling you. So we should draw things and think about attraction and repulsion, get the direction of the force, and then we know at this point that we have to add these. Okay, so part B then. At a certain point, the resultant field strength due to the 2-point charges, minus 2 microcoulomb and plus 8 microcoulomb, is 0. Will this point be found to the left of the minus 2, between the charges, or to the right of the plus 8? Explain how you decided upon this position. Okay, so we've already looked at a lot of what's going on with the fields. The field is going to be away from the positive charge and towards the negative charge. So we really need a redraw with fields further down the page here. So in the line joining the two charges, the field from the plus 8 is going to be away. So it's going to be to the left on the left of itself and to the right on the right of itself. The negative one is going to be a towards field. I'm going to use another color for it. So you're going to get something like that. So as well as that, the field belonging to the 2 extends out. Clearly the 2 fields are not going to cancel in this middle zone, so we can rule that out because they both point the same way. However, out to the right here, the field belonging to the 2 still points back in, and out to the left here, the field belonging to the 8 points back in. Points out that way. So they're opposing fields in these 2 zones, and really what we have to do is decide where they could be of equal magnitude. That's really the big deal here. So what you have to realize is that the field that's quite distant from the 2 over here will never be stronger than a field close to the 8, because the 8 will by its nature generate a stronger field. So this weakened version of the 2 field is never going to be strong enough. But a weakened version of the 8 might be, definitely will be, possible to be overcome by a field that's very close to the 2. So there will be a zone here where these can have equal magnitude. So this is where it's easier to explain if you break these into zones. Okay, so if you call to the left here zone A, the middle bit is zone B, and the right zone C. So you would then explain that zone A, they have opposite directions. Zone B gets ruled out because they have the same direction. Zone C, they have opposite directions. What you then say is that it would be impossible for them to have the same magnitude in zone C, so they could never have the same magnitude out here. So they do have the right direction thing, but not magnitude. They could have the same magnitude somewhere near the 2 here. And so directions are correct. Magnitude is a possibility, so this has to be the location that you choose. And hopefully you can use my explanation to compose your own answer to that. But really, you should draw it out because it's much easier to explain if you've got a picture to work from. 4a then, a cathode ray tube is an example of a basic particle accelerator. In the tube, electrons are accelerated from rest across a potential difference of 2.5 kilovolts. By considering the conversion from electrical potential energy to kinetic energy in the cathode ray tube, show that the electrons reach a velocity of 3 times 10 to the 7 meters per second. So this is straightforward, like QV equals half mv squared. So the charge is the electron charge because they're electrons, and we multiply that by the voltage that they are accelerated across, and that gives them their kinetic energy, a half times m times v squared, where v is the speed that they acquire. Now we will need the mass of an electron here, and we will need the electron charge, so we get those from our formula sheet. But basically, rearranging this for v, we need to multiply both sides by 2, divide by the mass, and take the square root. So we need to substitute into that. So we've got our 2, our charge of an electron 1.6 times 10 to the minus 19 coulombs, our 2.5 kilovolts, our mass of an electron, again these values both coming from the formula sheet, and put that through the calculator to see what we get. And so that does give us the value we were looking for. Part B then, the value of an electron mass on your data sheet is the mass of an electron at rest. It's called the rest mass, me. When moving at velocity v, the mass of the electron increases to a value m given by equation 4.1, and there you've got it, that it's the rest mass over the root of 1 minus v squared over c squared. Calculate the percentage increase in rest mass me of electrons travelling at a velocity of 6.2 times 10 to the 7 meters per second. So you can appreciate that's a reasonable fraction of the speed of light, because speed of light is 3 times 10 to the 8. So we would expect to see some kind of change there. So we should sub in and calculate this relativistic mass. So subbing in, checking everything in your equation is the correct value, remembering to do the squaring, etc., etc. And that gives us this value. So to get that as a percentage, we'd find the difference between the two values and put that over the correct value, or the rest mass value. Percentage difference then would be 9.31 minus 9.11 all over 9.11, and then multiply by 100. That lets us find the difference as a fraction of the actual value, and then multiply by 100 turns it into a percentage. And for that we get this value of 2.2%. Part C. In a synchrotron, charged particles are accelerated to velocities approaching the speed of light. Explain how a synchrotron operates to do these 4 things. So they want you, be very careful when you're asked to explain stuff like this, that you actually do look at the 4 things, and that your answer gives you a little bit about each of the 4 things that they were asking for. Right then, so let's go through these 4 aspects of the synchrotron. Firstly, the accelerating is done in the RF cavities. So be very clear about the fact that the particles are being accelerated. That's the first thing we were expected to ask, or answer, sorry. So yeah, particles are accelerated by electric fields provided in the RF cavities. So what about the circular paths? Well, we have steering magnets at various points along the beam path, and that's what helps to pull the circular motion that's required for the synchrotron. What about synchronicity? Well, the frequency of the RF in the cavities, it has to be adjusted to match the motion of the particles, because the frequency, as the particles get faster, the frequency isn't constant because their properties are changing. So it has to be adjusted to match that. And then finally, focusing the beam. And focusing the beam is done by what we call quadrupole magnets. By combining a series of quadrupole magnets, you can create a focusing effect. So again, remember in this type of question to look at the points that they've made and make sure that you've answered all of them. 5a. Certain subatomic particles are classified as leptons, others as hadrons. Complete table 5.1 below with an example from each class of particle and 2 differences between the particles. So this is a straight piece of memory work out of your notes. So the most obvious example of a lepton would be the electron, and the most obvious example of a hadron would be like a proton or a neutron. And the most obvious difference between leptons and hadrons is that leptons are completely fundamental and hadrons are composed of quark combinations. The second obvious difference is that leptons do not feel the strong force, whereas hadrons do. So if you know your particle properties, then these are easy marks. Part B. In the 1930s, the work of particle physicists such as Pauli and Dirac predicted a new particle called a neutrino. In order to prove its existence, an experiment was devised in which an inverse beta decay reaction would occur. An incomplete equation for this reaction is shown in equation 5.1. By applying the laws of conservation, deduce the charge, lepton number, and baryon number of the unidentified particle X, and hence identify what particle it is. Right, so we have to conserve charge here. So we need to look at what they have described for us. So we've got an electron antineutrino, a proton, a neutron, and X. Charges, then we need to figure out each one and put a wee equation together. So the neutrino has no charge, the proton is +1, a neutron is 0, and then we've got whatever the charge of Qx is, and so the Q of X would have to be +1. So now we do lepton numbers. The antineutrino is an antilepton, so it'll have an L of -1. That's not a lepton. The proton and neutron both aren't leptons, and then we need to figure out the L belonging to X. So looking at the lepton numbers, the L of X would also have to be identifiable from that, and it would have to be -1. So we're already looking at a positively charged antilepton. So let's do the baryon numbers. So the lepton isn't a baryon, so 0 here, +1 here, +1 here, and then we'll have to figure out X. And you can see from that Bx would have to be 0. So the most obvious positive antilepton would be the positron. And again, this is just following through very basic rules, so these are easy marks if you know your properties. Part C then. When beta- decay occurs in unstable nucleus, it will become more stable. Write the full equation for the beta- decay. So remember, in beta- decay, you've got a neutron decays to a proton plus an electron plus an antineutrino. And so you just write the equation for that. So we've got our neutron decaying to proton plus electron plus anti-electron neutrino. That is our beta- decay equation. Now you could do this in terms of like quarks and stuff, but I think they just want the basic equation here. Name the force responsible for beta- decay. So beta decay is the weak interaction. Again, that's just basic work from your notes. So very much these questions are based on your ability to learn the properties of. Question 6. A mass spectrometer is an instrument used to analyze the atoms present in a sample of gas. The atoms are ionized in order to produce positive ions and then pass through a velocity selector shown in figure 6.1. And so you can see this thing here. We've got a pair of plates with the bottom one positive got a known gap between them. We've got a uniform magnetic field acting into this grey area. It says the electric field is produced by a pair of parallel plates of separation D with a high potential difference V across them, as shown in 6.1. The velocity selector consists of electric and magnetic fields acting at right angles to each other, so that each ion is acted on by the vertical forces in opposite directions. When these forces are equal, only the ions with the velocity v pass through in a straight line as indicated. So this is what we would have called in the old days a cross fields experiment, with the magnetic field trying to turn the ions in one direction and the electric field trying to turn them in the other direction, and only the special group that have the right velocity will pass through undeviated. Write equations for the force acting vertically upwards and the force acting vertically downwards on a positive ion passing through the plates. So remember that they had the lower plate positive, so the electric force there is going to be upward on the positive ions. And the force on a charged particle in an electric field is E times Q, but we know as well from parallel plates that E can be written as V over D, so this is going to be like VQ over D. That means that the downward force has to be the magnetic force, and we can get it from like BQV, where V is the velocity of the particles. And just watch your capital V's that they look different to your small V's. Part 2 then, calculate the velocity of each ion passing straight through the selector when the magnetic field strength B is 240 millitesla and the potential difference V is 1100 volts and the plate separation D is 2 centimeters. So what we're going to do is put these two forces equal to each other, because that's when the ions will pass straight through, and then solve that for the velocity. Just be careful because we've got milliteslas and centimeters, so we need to watch our units here. The straight path then when the forces are in equilibrium. We put those equal, you can see the Q's cancel instantly, and we can rearrange that V, little v will equal big V over BD. So now we just carefully substitute into that. So 1100 volts divided by 240 millitesla times 2 centimeters, giving us this. Part B, a mixture of ionized lithium isotopes of velocity 4.8 times 10 to the 4 meters per second leaves the velocity sector and enters the shaded region of uniform magnetic field as shown in figure 6.2. The isotopes experience a force due to this field, which results in them striking the detector. Part 1. In what direction does the magnetic field act to make the particles follow such a path? Okay, so we need to have a look here. So remember, these are positive ions. We've been told that already. And they have to behave in such a way that they're feeling a force towards the center. Remember, that's the requirement of centripetal force, that it points towards the center. To give us this circular behavior, we would expect that. So that means that the entering particles at the top end here feel a downward force. So draw a little diagram for them. So a particle moving to the right, if it's positive, will behave like a current, and we can use Fleming's left-hand rule here. So on its entry to the magnetic field, it experiences a downward force. So in applying the left-hand rule, we have to put our second finger to the right here, our thumb pointing down, and when you get your finger into that position, or your hand into that position, you'll find that your finger is pointing straight out at you, which means that the magnetic field has to be out of the page. Part 2. How is information about the relative masses of the ions deduced from the detector? Okay, so this is related then to the idea that the radius of curvature in a magnetic field is a property of the momentum of the particle. So the radius of a particle moving in a magnetic field is proportional to momentum, and that means that the radius here will be proportional to mass, since v is constant. And that means that larger masses will hit the detector further down. The mixture of lithium ions contains the isotopes of lithium-6 and lithium-7 with masses of 6U and 7U respectively. The upper edge of the detector is 40 millimeters from the point at which the ions enter the field. Calculate the maximum magnetic field strength that can be applied in order for both ions to be detected. So the strongest field will produce the smallest radii for these two paths. So that's why they've told us the upper edge position. So this little tightest circle can be 40 millimeters. You can't have a circle tighter than that, or that particle will miss the detector. So this is going to be a radius of 20 millimeters. And you should really always try and draw things like this to try and figure out what's going on. So we've got a magnetic field producing a force BQV on the particles, and that is allowing them to make a circular motion. So we put that equal to the centripetal force value. So we have a magnetic force that has to be this size to produce this behavior. So getting B on its own, then we get mv over qr. So we need the mass of the lightest particle, and the radius that it will produce will be 20 millimeters. So we're subbing into that all the properties that we can gather from our formula sheet. The mass belonging to 6 U's, the velocity from the previous problem, the charge of 1.6 times 10 to the minus 19, and the radius of 20 millimeters. So just reminding ourselves from the formula sheet of the mass belonging to 1U, we need 6 of those in our mass. We had a velocity of 4.8 times 10 to the 4, and the charge and the radius from here and here. Just be careful that this one is in millimeters. And that gives us 0.15 Tesla. Seven A. Scientists wish to position a satellite in a geostationary orbit around the planet Jupiter. This is an orbit equivalent to a geostationary orbit around Earth. Give 3 characteristics of the path such a satellite would take around the planet Jupiter. So this is straight book work. You know, it has to have the same orbital period as the rotation on its axis period of Jupiter. It has to be in the equatorial plane, and it has to be turning in the same direction as Jupiter is rotating. So again, easy work if you've learnt this list off, and this is the kind of list that you should be learning off. They've asked this question quite a few times. You should know the routine. So again, if something is a short answer and can be learnt off, then it should be learnt off. Part 2. At what height above Jupiter must a satellite be situated in order to travel in a geostationary orbit? Take the mass of Jupiter as 1.9 times 10 to the 27 kilograms. The radius of Jupiter is 7.2 times 10 to the 7, and Jupiter's day length to be 10 hours. So always remember with these problems that you've got your planet, and that will give you a radius of the planet, so our Jupiter here. But you've also got the satellite orbit, and that gives you something that we refer to as the R belonging to the satellite. Okay, And then they're talking also about the height. So we need to be careful about those three things. So our Jupiter, our satellite, and H. Maybe I should have written H at a jaunty angle like that. Okay, so let's fix that. Okay, so let's write H this way round. Okay, so we've got R, the radius of the satellite orbit, the radius of the planet itself, and the height above the planet. So these two add together to give you RS. So it's just worth mentioning that the radius of Jupiter plus the height to the satellite gives you the radius to the satellite. So again, we've got a circular motion here. We've got the gravitational force providing a circular motion. So we put those equal to each other. So here we've got the gravitational force, mass of Jupiter, mass of satellite, at a radius out from the planet of RS. And we put that equal to the circular motion on a satellite of mass ms doing a radius orbit here. So we need to solve this for the radius out to the satellite and then work our way to the height above Jupiter. Now the mass of the satellite appears on both sides, so it can go immediately, and then we rearrange this. Now if we remember that omega squared can be written as 4 pi squared over t squared, because omega can be written as 2 pi over t, then you know this consists of 4 pi squared over t squared. Now we're going to bring these r's together and then take a to get rs. So we need to bring this 4 pi squared over t squared over to this side. So we'll have a g and an mj and a t squared on the top line. And we're going to end up with a 4 pi squared on the bottom line. Now we need to sub into all this. G times mass of Jupiter times t squared, and t is going to be like 3600 seconds times 10 hours, and then square that, and dividing by 4 pi squared. Sorry, that mass should be 1.9 times 10 to the 27. And always get into the habit of scanning over your numbers before you pump it into your calculator. Just check that everything is what it's supposed to be. You know, that this matches the G value in your formula sheet, that this matches the number they've given us, that this matches what 10 hours would be, and that everything else is correct before you pump into calculators. Now we need to find H. Okay, and there are a lot of marks for this, but there are a lot of bits. So be careful. We can all make mistakes. Part 3, calculate the linear speed of the satellite. Well, there's loads of ways of doing this, but you could probably go for v equals r omega at this point. So subbing into that gives us that. Part B, the geostationary satellite has a mass of 300 kilograms. Calculate the weight of the satellite at this position above Jupiter. The weight of the satellite will be the force of gravity at that point on it, so it's just a gmm over r squared. And that gives us like 1467 newtons. Now the mark scheme suggests that you work out the field first and then do field strength times mass, but that seems ridiculously wasteful of time when you can go straight to the force from this equation. And the force of gravity on an object is its weight. 8a. In the space below, sketch and label a diagram of a step-up transformer. So you're going to have an iron ring and 2 coils. And we need to show more coils at the secondary. Something like that. Part B. Step-up transformers are an important part of the national electricity supply grid. One such transformer changes the voltage at the generating station before electric current is transmitted over long distances through power lines. It has a turns ratio of 20 and a current of 0.045 amps is required in the power lines. Calculate the current that enters the transformer on the primary side. So firstly, the secondary voltage will be 20 times the primary voltage. And if the transformer is 100% efficient, then the VSIS will equal VPIP, the power out equals the power in. And then subbing in the voltage relationship, Vs can be written as 20 Vp. And at that point the Vp's cancel. So 20 times 0.045 is going to come to 0.9 of an amp. The electrical power entering the primary side of the transformer is 22.5 kilowatts and the transformer is 95.5% efficient. Calculate the voltage at which the electricity is transmitted across the power lines. Okay, so we need VP IP times 95.5%, giving you VSIS. So it's like power in times the efficiency gives you power out. So the VPIP is the primary power, 22.5 kilowatts. So Vs is going to be that value over Is. Giving us that value. Part 3 then outline 3 causes of energy loss in transformers and state how the loss is minimized in each case. So you've got your various kinds of losses. You've got I2R losses in the coils. You've got magnetic leakage in the core, where the field from one coil isn't reaching the other. Not all of it anyway. You've got magnetic hysteresis in the core itself, and then you've got eddy currents flowing in the iron, and each one of those has a suitable counteract that we have to do. For example, with the wires you pick good copper and you make it thicker where you're expecting more current. With the magnetic leakage you wind the cores in such a way that they're on the same center pole rather than on the 2 outside that we would draw. Magnetic hysteresis, you pick good quality iron, and for eddy currents you make sure that the core is a laminated of layers of iron so you can't get current flowing across those layers. So this is the list that they are looking for, 3 of these things and its correction. (9a) Part 1. State Faraday's law of electromagnetic induction. So we state that the induced EMF is equal to the rate of change of flux linkage, or you can say it's proportional to the rate of change of flux. State Lenz's law of electromagnetic induction. So we've already stated how it's related to flux linkage changes. What we need to now state is the direction information that comes in Lenz's law. So we state that the EMF is induced in such a way as to oppose the flux change causing it. So that means that whatever it does, it will oppose the flux that's coming through. So for example, if you're moving a magnet near a coil, it will always oppose the motion of the magnet. If you let a current flow, it'll produce its own poles to oppose that. motion. Part B, a bar magnet was dropped through a multi-turn coil as shown, and the coil is connected to a data logger which records the EMF. The EMF induced in the coil varies with time as shown. So you can see what happens here. The coil is accelerating because of gravity. So it comes through, produces an EMF, and leaves a little bit quicker because it's moving faster at the end than at the beginning. That's what the difference in these two bits of the graph are all about. So slower, gradually becoming faster. So the behavior on the way in is slightly slower than the behavior on the way out. Part 1, explain why the data logger is used to record the EMF in this experiment. So I'll just bring back the graph to show you. So you can see that the time scale on the graph here is like 80 milliseconds. So all these values would have been taken in a tiny fraction of a second, and that's why we need the data logger, because the data is over a very short time scale. So something along those lines. Data comes in much too quickly for a human to record. So now they want us to explain the shape of this, and we are supposed to refer to both Faraday's law and Lenz's law. Now Faraday will refer to the height of these peaks because it's all about the magnitude of the EMF. Lenz will be talking more about the directions of them, the positive and negative values. So it's worth noting that there are 5 marks here, and so taking your time about this is important. So we need to talk about the fact that it's accelerating, which explains why the second peak is bigger than the first peak. We need to talk about the fact that it's going into the coil in one case and out of the coil in the other, which gives you the reversal of directions. So this is what the mark scheme is looking for. So they mentioned that you've got a bigger peak on the output on its way out because it's leaving. It's moving quicker as it leaves. The idea that the rate of change is increasing, and that's what's giving you a bigger peak at the output. The idea that it will oppose the motion on the way in, and that the polarity will reverse on the way out so that it can still oppose, and that causes the EMF value to reverse. So the reversal corresponds to this moving quicker, so we get a bigger peak on the way out. And you can see they're looking for various aspects of that to get all 5 points. So now they want to know about how the graph would be different if the magnet was dropped from a position further above the coil of wire. Okay, so it's coming in from a higher point. It will have reached a higher speed by the time it reaches the coil. So both peaks will increase in size, but they will reduce in duration. Okay, so the time duration will shorten, but the peak sizes themselves will increase. And then if you drop it from the same height but with a greater number of turns, then the time scale of all this will stay the same. It's just the sizes of the peaks that will change. So in this one, both the time scale and the sizes will change. In this one, just the sizes of the peaks, the magnitudes of the peaks. And that's it. Thanks for watching.